All right, so the next thing that we're going to be talking about is chapter 16. We'll be talking about in this chapter solubility and complex ion equilibrium. As always, the practice problems are going to be on slide 1. All right, and you guys can continue to turn those in for up to 10 points back on your quizzes if you get less than a 75. All right, transitioning to our slide 2, right, solubility is connected to equilibrium. All right, so as you know, not all solids are going to be completely soluble. They're not going to completely dissociate, right? And some will dissociate a little bit, like magnesium hydroxide or calcium hydroxide. Those are going to dissociate only a little bit, so they're not very soluble. And then some are going to dissociate a lot, like calcium nitrate or potassium hydroxide. All right? Now, when a solid doesn't dissociate a whole lot, or doesn't dissociate fully or completely, right, it establishes an equilibrium. Okay, so for example, calcium hydroxide, solid, when put into water, okay, will form Ca2 plus aqueous plus 2OH minus aqueous in a small amount, right? Calcium hydroxide is one of our salts that is not very soluble, right? Remember, calcium is one of our exceptions, just like magnesium, right? Hydroxides are usually insoluble, okay? But this is weakly soluble, so it's going to establish an equilibrium, right? If it were fully soluble, right, like say we had potassium hydroxide, right? If I add that to water, right, it's only going to be a one-way arrow, which is to fully dissociate, okay? Because this is completely soluble, all right? Calcium hydroxide, on the other hand, is not completely soluble, and so it forms an equilibrium, all right? And if I were going to be a betting man, I would say that our large arrow points the other way, saying that that is mostly a solid, okay? So, as such, right, since it forms an equilibrium, it has an equilibrium constant, specifically for its solubility, okay? And we call that KSP, which is equal to Ca2 plus, right? That's our concentration of calcium 2 plus, and our concentration of OH minus squared, right? Where we've used our stoichiometric coefficients of 1 and 2, all right? And then that all goes over our concentration of calcium hydroxide as a solid. Now, if you remember, an equilibrium constant is not going to have solids unless everything in the reaction is a solid, okay? So we will leave out our solid, and our KSP for this will simply be our 2 aqueous species, okay? This is called, our KSP is called the solubility product constant, okay? And it's called that because there are no reactants, right? It's only products, and it's our solubility reaction, okay? So now let's transition into how we use this, okay, on slide 3. Okay, so let's calculate our KSP. An example of that would be the concentration of silver plus at equilibrium is equal to 2.2 times 10 to the negative fourth molar in a saturated solution of silver chromate. All right, so let's calculate our KSP for that silver chromate. All right, now for our solution, right, we know that this is going to be an equilibrium problem, right? Since we're talking about our KSP, we know that that's our solubility product constant, which has to deal with equilibrium. And since we are doing an equilibrium problem, that means that we will need an ice table. Again, we're reusing those same concepts that we've done for the past several weeks, just with a new type of problem. All right, so let's set up our ice table. All right, so that'll be step one. So we have Ag2, oh, I'm sorry, not chromate. Actually, I want it to be C2O4. Okay, so silver oxalate, is that right? I think that's right. C2O4. And then that's a solid. We will have put it into water. Okay, and it will be in equilibrium with 2 Ag plus, aqueous, plus C2O4, 2 minus, aqueous. Okay, again, we'll be putting our solid first, and then our dissociated ions, so solid on the left, and aqueous on the right. Okay, and ICE. Okay, now since we started out with our solution, right? This is at equilibrium, okay? So that would be at our bottom of our table, so we're not going to use that yet, right? We also know that this is solids, okay? So step 2 is going to be to eliminate solids. Okay? Step 3, as always, we're going to work our way down the table. Okay, so we're going to start out with none of these because we have none of those initially, right? That's at equilibrium, okay? Then we work through our problem as always, okay? So we have 2 times plus x, remember it's on the product side, 1 times plus x, all right? So we're going to have x and 2x. Our next step is going to be to write our KSP, okay? And our KSP is equal to our concentration of Ag plus squared times our concentration of C2O4, 2 minus, okay? Then we're going to evaluate with our equilibrium, right? So that's going to be KSP is equal to 2x squared times x, right, where I've put in what my concentrations are from the table, okay? Again, we're not putting these numbers in until later, right? We're always going to start from our beginning reaction and work our way through the table. Okay, so now we've got our KSP, right? So it's going to equal 4x squared times x, which is equal to 4x cubed, okay? Now, we also are looking for our KSP value, right? Now, it specifically said that our concentration of Ag plus at equilibrium was equal to 2.2 times 10 to the negative fourth. Okay, so this is where we use our extra information. Okay, so we know that the concentration of Ag plus at equilibrium, right, that corresponds to 2, right? We know that this is equal to 2.2 times 10 to the negative fourth, all right? And that at equilibrium is equal to 2x, right? So now we can solve for x. X was equal to 1.1 times 10 to the negative fourth, right? That math should be pretty easy, okay? And then we just plug that in to get our KSP, right? Where we have 4 times 1.1 times 10 to the negative fourth cubed, okay, which gives us a KSP equal to 5.3 times 10 to the negative 12, right? So not very soluble, okay? Again, that's telling us how likely it is for us to be in its dissociated state versus its solid state, okay? I'm sure that you guys probably want another example. Okay. Last time we looked at calculating our solubility product constant, so our KSP, our equilibrium constant for solubility. Okay. Now, looking at slide 4, now we're going to calculate our solubility. Now, our solubility is how many moles per liter, okay, so that's going to be our molarity, how many moles per liter of our solid dissolved. Okay, so again, this is going to be an equilibrium problem. All right, so let's calculate the solubility. Again, this is different than our KSP, right? Our KSP is our solubility product constant. Our solubility is going to be how many moles per liter of our solid dissolved. Okay, so let's calculate our solubility of lead 2 iodide. Okay, and lead 2 iodide has a KSP equal to 1.4 times 10 to the negative 8th. Okay, so our solution, right? We're going to be setting up an ice table. We know it's equilibrium, right? So our ice table, right? For a reaction, we want to know how much of lead 2 iodide solid dissolved. So we're going to add that into water, make our equilibrium. And what do we think it's going to be? It will end up being lead 2 plus aqueous plus 2 I minus aqueous. Okay, again, we're writing our dissociation reaction when we add it into water. All right, now I just put the water up above. You could put it there, but we're going to end up canceling that column out anyway, right? So let's write it above. Excuse me. And we have our ice table, ICE. Okay. Now, what are we going to do for our second step? That's right. We're going to take out all of our solids. Okay. So this column goes away. All right. Step 2 or step 3, right? Or not step 3, but as we fill in our table, right? 0, 0. We know we started with none of that, right? We use our stoichiometry. 1 plus x, 2, right? 2 iodide, so 2 plus x. So we have 2x and x. Step 3 is our KSP, right? We're going to write that symbolically, right? So that would be PV2 plus times our I minus squared, right? Let's not forget that we still have to square that, okay? And I've left off my solid, okay? Step 4, right? Write it with our x's. So that's going to be x times 2x squared, 2x quantity squared, excuse me. Okay, so that's going to be 4x cubed, like we saw last time. Okay, so we also know, right? So now our last step is to use the extra information to solve for what we don't have, right? So we know that 4x cubed, right? So this is going to be KSP. KSP equals 4x cubed, but it's also equal to 1.4 times 10 to the negative 8th, okay? Which means that we can then solve for what our x is, okay? X in this case is equal to 0.00152 m, okay? And that corresponds to our concentration of Pb2 plus at equilibrium, okay? Now, from this, right, we need to use our stoichiometry to convert, okay? So, I'll write this above, right? Convert to a concentration of our salt, okay? So if we want to convert that into our concentration of salt, okay, this will be our concentration of salt that dissolved, okay? So we have Pb2 plus is equal to, right, our concentration is going to equal moles of Pb2 plus per liter, right? So I can take 0.00152 moles of Pb2 plus, right? That's where that came from because we have molarity per 1 liter, okay? And then I'm going to use the fact that 1 mole of Pb2 plus had to come from 1 mole of Pb2 iodide, so PbI2, all right? So that means that my concentration of PbI2 is equal to 0.00152 moles per liter, right? Which is molarity. This is my solubility of the salt, okay? All right. So we talked about that. Our next thing that we want to talk about is relative solubilities. Okay? This will be slide 5. Okay? Now, let's say that we want to know which of 2 salts is more soluble, right? Like, is sodium chloride more soluble than calcium molybdate? Well, yes, because sodium chloride is completely soluble, right? So that one was easy, right? But what if it's not so easy, right? Well, we can always use the KSP and set up an ice table, right? That was just like what we did in our last example, right? So we could set up our ice table and figure out our solubility, right? Remember we found our solubility of our PbI2, right? We could do that for any salt by knowing our KSP and setting it up in our ice table and then comparing the 2 solubilities, right? The bigger number there would be more soluble, right? That meant that more dissolved, okay? Or, right, sometimes, and I stress this, sometimes we can just look at the KSPs. Okay? You cannot always do this, okay? But sometimes we can. All right, I'll explain how we know when we can do that. All right, so we can compare the KSPs if both salts that we're comparing produce the same number of cations and anions. Okay? So, for example, right? Let's say we want to know if copper iodide or strontium sulfate is more soluble. Right? Well, if I look at my KSPs, right? KSP is equal to 5.0 times 10 to the negative 12, and KSP is equal to 3.2 times 10 to the negative 7. Okay? Now, when we were talking about acids and bases, right, we said that we could just look at our KAs. Okay? Well, that's not necessarily going to be the case for our KSPs. Okay? And that's because they're going to produce different amounts of the ions. And remember, we used our ions to figure out our solubility, right? We found our concentration of our ion after, right, at equilibrium, and then we related it using the molarity at the end. Okay, so the way that we do the KSP method is we're going to write our dissociation reactions for each salt. Okay, so CuI in H2O becomes Cu2 plus and 2I minus, or sorry, and just 1I minus. Okay, so there's one, right? And then that's versus our strontium sulfate, which was Sr2 plus, or sorry, SO4. Getting a little ahead of myself there. We put that into water, and we have Sr2 plus plus SO4 2 minus. And again, these are in equilibrium with each other. We haven't completely gone to just having the ions. Okay, we still have some of our solid. Okay, they're in equilibrium with each other. Okay, now the next step is write our KSP expressions for both, right? So the expressions are going to be Cu2 plus to the first, I minus to the first. Again, I'm going to stress that this is the expression step. Okay, and then we'll have a KSP over here for strontium sulfate of Sr2 plus to the first and SO4 2 minus to the first. Okay. Then we're going to plug in, right? So we're going to use stoichiometry to relate to X. Okay, so this would be like the ice table. Okay, so we have KSP is equal to, in this case, we have an X, right? 1X. We have an X here. Okay, and over here, right, so this would equal X squared. Over here, we would have KSP is equal to X times X. Again, just like our ice table, X squared. Okay, if these are the same, right, then compare your K's, right? And the larger is more soluble. Okay, so in this case, they had the same form, right? So we're going to choose the larger of these two KSPs. this is the larger number. 10 to the minus 7th is way bigger than 10 to the negative 12th. Okay? So that means that strontium sulfate is more soluble. All right. So what does it look like if this doesn't work? All right. Remember, if this doesn't work, then we'd have to do an ice table for each of them and then find the solubilities and then compare. Okay? So an example where this may not work, let's do one, right, would be where we have copper iodide versus lead 2 iodide. Okay? So if I'm walking through, my first step is to write out my reactions. So I have copper iodide, put it into water. Then I've got Cu2 plus aqueous plus I minus aqueous, okay, versus Pb, and I'm going to write that down on our next line. We have Pb I2, throw that into water, okay, and we'll get Pb2 plus and 2 I minus, okay? So if I then write my Ks, right, my KSP for copper iodide, right, that in the expression form is going to be Cu2 plus to the first times I minus to the first. My KSP for lead iodide is going to be Pb2 plus to the first and I minus to the second, okay? Now, right away, you can already tell that they're not going to be in the same form, okay? So if they're not in the same form, then that means that you're going to want to use an ice table right away, okay? If you wanted to continue with all the steps, your next step would, of course, be KSP equals X times X, again, using your stoichiometry, right? And then, and of course, that one is for copper iodide, and then the KSP for lead iodide would correspond to X times 2X squared, which was 4X cubed. Okay, at this point, you can guarantee that they're not in the same form. Okay, so again, you'd have to do an ice table. Okay, this would be a case where you cannot simply look at the Kas. All right. So with that, that will conclude this first part of our lecture for today, and I hope that you join me for the next half.